Stacks and queues are two most useful data structure. Both of them belong to list data model. Today we are going to talk about queue data structure. You know that none of the programming language supports queue as a built-in data structure. So today we are going to talk about how this queue data structure will be represented using C language programming notations. In this context, we are going to propose two important schemes for representing queue data structure, and then we'll try to implement various functions related to queue data structure. But before going to start, let's have a formal definition what a queue is. That in the queue data structure, all the elements are inserted at one end and they are deleted from the different end. In a stack data structure, all the operations take from only one end, but in queue data structure, elements are inserted from one end, let's call it a rear, and deleted from another end, let's call them front. Sometimes it is also called that queue is a first in, first out data structure. So in brief, it is called FIFO structure. Diagrammatically, we want to show you how queue is basically represented. Basic purpose of this diagram is to show you that when you try to implement queue data structure, you require more than one variable. When you implemented stack data structure, you had only one variable called top, which pointed to top of the stack, because all the operations were taking place from only one end. But when you are working with queue data structure, you require two elements to operate. One will point to the current element of the queue, that what we call the rear, where all the insertions are going to take place, and another will be a front. Here you see the front. So front will always point to the location where the element is going to be deleted. We'll talk about this two in quite detail. Before coming to this one, how front will be used, how rear will be used, let's be very clear in what type of situations we are going to use queue data structure. And there are many other applications one can think of, but two most useful application of a queue data structure is, one is what we call them scheduling for jobs, and second is called simulations. Now let's talk about in brief what we do mean by scheduling of jobs. Most of the operating system on which you will be working, for example, Windows 95 is one operating system, Windows 98 is another operating system, Windows NT, Unix, they all are operating system. All these operating systems are also called multitasking operating system. Single CPU handles number of tasks. So all the tasks basically compete for CPU time concurrently or simultaneously. But since CPU is only one, it can handle only one task at a time. So all the tasks which wants to take CPU time, they have to put into certain queue depending upon the policy of operating system for scheduling of jobs. So queue is a data structure which is used for scheduling of jobs or scheduling of tasks to be executed by central processing unit. This is one application, and we will show you certain diagrammatic representation of scheduling of jobs by any operating system. The second, another important application of a queue data structure is in which you will be also involved, that is called simulation. Simulation is a program, is a computer software which describes the system of certain entity. For example, you can simulate how does airport work. Basically, the purpose of simulation of the airport will be to find out that how queue is basically formed, on what counter you have a bigger queue, at what counter you have a smaller queue, at what time you have a bigger queue, so that more people should be deployed to serve the queue. So this way one can examine the behavior of certain system. For example, if you want to work with computer and you don't have a computer, then you can write a simulations program which will show you how to work with a computer. Even if you want to learn driving, today there is a simulator, there is a program through which you will be able to learn how to drive a car before actually you enter into the actual driving exercise. So now these two are important applications, and these two are basically left as you move further. When you learn operating system, some of the simulations program will be discussed. Now let's take up this problem once again, that how the front and rear are basically behaving in a queue type of data structure. Now just you notice one thing, I told you that whenever we insert, the rear always gets advanced. For example, just assume that in beginning both front and rear are pointing to nothing since there is no element into the queue. Moment you insert first element, the rear will point to A. Insert second element, now rear will advance to the next position, now rear is pointing to B. You further add another element, let's say call it C, then rear will be basically pointing to the next element. Let's add another element. Now D has been added, rear has advanced to B now. So as you are inserting new elements, rear is getting advanced. Now moment to try to remove elements from the queue, front will be incremented. Now A has been decremented, A has been removed from the queue, now front is pointing to B. If you delete B from the queue, now front is pointing to C. It means front value will be again advancing now. So when you write simulate data structure related to queue, basically you have to keep on advancing either rear or queue depending upon what operations you are doing. Now once we understood what a queue is and what are variables are required to maintain the operations on the queue, let's try to talk about now how to design a queue ADT. Now before coming to actual programming, this is the paradigm we are following. But first we have to design ADT. ADT is a stack model which is independent of any programming language. The purpose of ADT is to provide modularity of your program. Any ADT will contain the data structure related to it, as well as what are the operations which are going to work on this data structure. Now it contains two components. Any ADT you define, either you define ADT for a list, either you define ADT for a stack, it must contain the representation scheme, how a stack or queue is going to be represented. Now here simply we are writing that we require a list. This type of structure we require to represent a queue with 0 or more elements. This is the one structure, and later on we'll try to refine them in terms of actual programming construct. So the basic structure of queue as well as a stack is a basically list model. This is what we have written as a part of object or part of a structure for a stack for queue ADT. Now what are the operations we have to do on the queue? Again we have to keep on adding all the operations here itself. So the first operations will be create a queue. If you want to add something into the queue, first you have to create a model for it. So I will be writing a function for create a queue, and the size of the queue will be again depending upon how much memory you are available, you have got access to, what data structure you have used, whether it's flexible data structure or dynamic data structure you have taken. So simply, so the queue, this function will contain a logic for creating a queue, data structure, and the create function which size will be according to the size you have given to as a part of global declaration. Let's add some more functions to it, because when you want to implement a queue data structure, you have to add many more functions to it. The another important function will be clear queue. This is just you see in this slide where I have written another function. This is a second function. The purpose of this clear function is to make the queue empty. Suppose we want to clear the queue, for example, then all the elements have to be deleted from the queue. So simply I have written into a program. This statement is independent of any programming language. Basically I am giving you a rhythmic descriptions of how to go about it, and depending upon the knowledge of your programming language, you will be basically translating them into that language. So make the queue empty. Like for example, if you remember from the stack, how we will make a stack empty? When the top becomes -1, a stack becomes empty. So again here you have to think in terms of how to handle the rear and the front variable to make queue empty. Let's have more functions to it. The most important function which you are going to work to do on queue data structure is add. So suppose that I want to add X element into the queue. So add is a function which adds element X into queue data structure. Now what I have to do now before putting the element into the queue? First I have to check whether queue is full or not. If queue is full, means all the spaces are exhausted, then you can't put any element into the queue. This is what we have written. If queue is full, return false. Otherwise, you add element to the rear of the queue. That is what we have seen from the previous diagram, that each time you insert the element, your rear has to be added, rear has to be advanced. So means you are adding each element into the queue at the location pointed to by rear. And then finally you return true, indicating that additions operation has taken place. Let's have is empty. Is empty is another functions we have defined as a part of my ADT model now. Is ADT it returns a Boolean value, either true or false. It will be used by some of the operations of queue. Is empty means it returns true if queue is empty, and false otherwise. It returns either true or false. If queue is empty, no element is there, then it simply returns true, otherwise it returns false. Is full is another function. We check whether the stack size is full or not. Then if a stack size is full, if all the elements have reached to the maximum queue size value, then you have to return true, otherwise you have to return. So all these functions will be used by either push function or by pop function, or let's say either by add function or by delete function. The delete, again, what it contains two arguments. Again, what we are talking about is the algorithmic description of the function. We are not writing them into any programming language notation. So this is the best way to write a program. First you try to understand, first to design a good algorithm, good ADT, and then only you start writing a program. So when we are writing is empty queue, this is empty is a function which already defined, and this is another way of writing a program. Rather than writing everything into each program, whether you design a program into a smaller function and call those functions wherever you need them. This basically shows the reusability of your program. So I am calling them. Delete means if queue is empty, you can't delete anything. This is what we are checking. If queue is empty, you return false. Otherwise, you assign, delete, set x to the value of element at the front of queue. Whenever you are deleting any element from the queue, you are basically deleting from the location pointed to by front. So front will be used to delete any element and assign, in this case, assigning to the value x. So x is a location where the deleted element from the queue will be assigned to it. So these were two major functions we will be able to complete now. Now once we know what is ADT and how we are going to represent them, now finally we have to think in terms of actual representation. ADT is not actual representation. ADT is just to understand. It is basically model which is nearer to programming language implementation but not actual implementation. So now since you have understood how front queue is working, how various functions will have to be written to it, then you have to implement them into actual programming language notations now. Now if you remember, we implemented list data model, we implemented a stack data model, and for representing all these two data models, we used one data structure, what we call them sequential representation, or let's say call it array representation. So we implemented stack using array data structure. Again, array means sequential representation. We implemented list data model, and also we represented it through this one. Let's continue with the same trend and try to find out whether the sequential representations scheme for a queue data structure is sufficient enough or not. But you will see later on that it's not so easy to represent queue data structure sequentially. The sequential representation or array representation of a queue is not a very ideal solution. Number one. Number two is that here also you have complexities added because of you are working with more than one variable. Here you have two variables, front and rear. Now in this table, I just want to show you that how job scheduling is done in operating system. Now here is that this has got 1, 2, 3, 4, 5, there are 6 columns are there. One is called front, second is called rear, and then the size of your stack is Q0, Q1. So there are 4 elements. In the size of the stack is just 4 elements now. Now in the beginning, both front and rear is not pointing to anything, no element is there, so they are basically -1, -1, -1, -1. Same scheme I used when I was talking about a stack representation. -1 means that no element has been inserted into queue. Now moment you insert first element, let's say the J1, first element has joined the queue, then it will then rear will be advanced. Now -1 plus 1, it becomes 0. Now this is what we have written. Job 1 is added. Let's add more now. Now J2 has joined. Again J2, moment you insert a new component, again rear will be advanced. Now third element has joined, rear has been advanced now. Now just notice one thing. Now we are trying to delete some element, right? Now in start everything from one end. Here deletion is from another end, which is being controlled by front now. Now moment to delete J1, just see over here, moment I am deleting J1, then what will happen? Your front will be advanced. You delete further, now you deleted J2, again front has basically advanced. Now here the purpose of this one is that how rear and front are changing its value after deletions and insertion. But the most important thing is like this. The J3 has come to Q2. Now the value of rear is 2 now. Now as we insert more elements, the Q is advancing towards the right. Now eventually your Q will be full. Now moment you add one more element, let's say J4, your Q is full. But if you see this diagram minutely, you will see that although the rear comes to the maximum Q size, but still you have 2 spaces empty. And that is what I was talking about, that the sequential representation is not very ideal. Now what you have to do now? What you have to do is that you have to keep on shifting the array. You have to keep on shifting the element into the this sequential representation. So one of the important drawback is that all the time we have to shift the elements. So the shifting is a time consuming operation, and each time you shift your elements and you have to shift it, there is no other alternative, because otherwise your queue is not fully utilized. And the second disadvantage is that each time you shift your queue, then rear has to be recalculated. Rear has to point accordingly, point to that locations accordingly. So this calculation of shifting and recalculation is a time consuming operation. So queue structure of this type will be not very efficient now. Let's see the worst type of situation when the queue size is very large. This diagram contains more elements. The similar exercise, but size of the queue is very large. I have just put them Qn. N might be thousands or millions or whatever be. Now here just think of that if we keep on shifting a large set of elements, then queue will be very slow. All the operations on the queue will be time consuming operation and so on, just like it become a manual type of operation. But anyway, let's try to understand now. Now we have here is the basically -1, is the say here, the front value first time in first row, -1 means that no element has been deleted so far, and the rear value is n-1, means that your queue is full. So we have J0 to Jn1, means all the elements have been put into the queue, no space is left. Now what we are doing now, so now first element is going to be deleted, here we have written the action is J0 is deleted now. If J0 is deleted, your front will be advanced. Now you just notice the first column, front has become 0. Since you delete the element, again J1 will move to the first position, J2 will move, right? Accordingly all the elements will be shifted towards left. So this is what we have written. Add, I have added some new element called Jn here, okay, and job J1 to Jn-1 are moved. So each time I insert one element, I am moving remaining elements. If the size is very large, then the movement of operation or shifting of operations will be very time consuming. And the complexity, what we call the worst case complexity, is order of maximum queue size. If the size is very large, then the movement of operation or shifting of operations will be very time consuming. So now the best scheme for representing queue data structure is called circular array. Now think of array as a circular now, or let's call them circular queue. If the rear is pointing to n-1, if next element has to be inserted, you don't need to shift the elements. The next element will be inserted at the Q0 and and in this case rear value will be 0. When front and rear are 0, your queue is empty. Now one major change has come, that when I was showing you previous table where rear and front were having -1. Now when we are talking about implementing circular array, then front and rear will be initialized with 0. So if both are equal, it means queue is empty. Now let's see another example now. Another example here, we have put 3 elements into the queue, job 1, job 2, job 3, then rear has advanced to 3. Let's have another different representations, and then finally we will come to how to implement them into actual programming language notations. Now the second diagram, it says when your queue is full, it means that rear will be 5 and front will be 0. And similar exercise has been done here also. One important point to be noticed here is, just in this case, even if one location is free, but we have to show them that we can't push further element into the queue, because this is what we have agreed upon with the previous diagram, that the queue will be empty only when front and rear will be equal and both will belong to 0 now. So in this case, again we have to agreed upon one rule, that even if in case of insertions, queue will advance only from n-1, not more than. Otherwise, we will not be able to differentiate between queue full and queue empty. And we'll take up this concept when we start writing a program. So here in this diagram, once again, we have shown you 2 full queue. So real advantage of a circular queue or based on circular array is that representation is very efficient, right? And this is because of that you don't need to shift any array elements. The most important thing is, which you have to see, that the additions and deletion in circular queue or circular array will be much more difficult than additions and subtraction of a queue which is represented through represented sequentially. Because here you have to maintain the rotations, you have to maintain the occurrence of rotation. And how the occurrence of rotations taking place into this queue? It is because you can see these 2 expression which will be used while writing additions and deletion from the queue. This says this expression is rear equals rear plus 1 mod n. Mod is a modulo operator which gives you remainder value. The meaning of this expression is that if rear becomes n-1, the next element will be at first locations at 0th positions if that location is empty. Otherwise, you keep on advancing the rear clockwise. Same thing we have to do with the front. So here both rear and front has to maintain the circular rotations now. Again, front will be also written in the same design, because if you keep on removing the elements, front has also moved into the circular position. So this expression shows that both front and rear has to move into the clockwise positions, and from the end it has come to the first rather than shifting. So if we do this type of operations, if we follow the circular array representation, then all the operations will be done into one time cycle. So here we have written order of 1. There we have written order of maximum queue size. The meaning will be all the operations will take n amount of time, and n will be depending upon how many elements you have put into the queue. So it is much more faster, efficient and elegant schemes. Now let's go very quickly. Now we are not going to write into actual programming language notation, because understanding the algorithm is much more important. So we are just writing in a much more descriptive manner. Now here is that I am writing a function called add queue, which will insert an element into the queue, and its arguments are int item, the item which I want to insert into the queue. Queue is queue. This is the name of the queue data structure which is defined. N is the number of elements you can put into the queue. This is the front and this is the rear. So right? So we have to handle the front and rear very well. So this is what we explained here, what we are trying to do. Insert item into the circular queue, stored into this queue n, rear points to the last item, and front is one position counted clockwise from the first item. You can see this one from the previous diagram and so on. let's try to see what will be my logic, the same logic, because when I am trying to insert the element, I have to maintain the rotations through rear, so I am writing rear equals rear plus 1 mod n advance. Then it basically the purpose of this statement is to advance rear clockwise. If rear becomes n minus 1, automatically it moves to rear 0th positions now, right? If front is equal to rear, then Q is full. Now here this is another situation now. So front is equal to rear, is again Q will be empty, but front is equal to rear, again Q is full. So these two situations you have to understand, right? So this is basically, and then I am assigning the item into the Q rear, right? So item will be now once is right. Otherwise if the element, if Q is not full, then simply item has to be assigned into the Q rear, into that positions. Now let's see now how delete is going to take place. In delete Q, I am removing the front element from the Q. This is the basic objective. It has same arguments as the previous one. This is Q, this is number of elements, this is the front, this is the rear. So the basic logic will be, if front is equal to rear, then again Q is full. Otherwise we keep on advancing the element and assigning the element, assigning the value into the item. So this item is the position where I want to store the element which has been deleted from the Q. This is the basics. So which one I am maintaining the rotations operations. Now, so this is what we have a circular, how we represented sequentially based on circular array concept. Let's have another scheme now. So we are proposing the two schemes for Q data structure implementation. One was circular array based, and the second is, and accordingly we wrote all the functions Q empty, Q full, Q clear, and so on. Now let's talk about more dynamic model we'll try to present now, and this dynamic model is your Q is based on linked data structure now. Now here is what we are talking about is, let's have another model now. This model is what we call a linked list representation of Qs now. Here is, it is very similar to when we represented list data model now. In this case is that the list is a self-referential structure where list is a pointer pointing to a struct type of definition which is not defined there, which is defined little later on. So the node contains two elements, one is the actual data and the second is pointing to the next element. So our Q will be also based on this model itself. I will be using this model for defining my Q data structure, because Q data structure is also similar to a list data model where there will be element and the next element will be stored into the next locations now. So one thing before going forward with linked list data representation is that when we say linked list data representations of any data structure, it's a dynamic representation, and all the elements are not stored at one position, they are stored at different positions and they all are being linked with a pointer. But when we say sequential representations through array, all are stored at one position. Anyway, all these points have been discussed in detail. Let's come back to how we move with your linked list based data representation for a Q. Now, so my Q is also similar to a list data model, right, which will contain two elements, front and rear. Of course the element is there and both are basically pointing to this type of data model. So our linked list Q is similar to list, except here you have two other elements have been added to it, front and rear. So this is a Q data structure of linked list type. Now let's move very quickly now that some of the operations we are going to do on the linked list data model. Now earlier we represented all the function which we defined, it was based on sequential representation. Now we have my ADT is going, my actual structure of Q will be represented through linked list, and now all the functions will be written accordingly. So when you change your data structure, your function, the way you write your algorithm or function also will change now, because the elements of storage are different. The way element have been stored now is different from the element were stored into the sequential representation. So let's talk about how we clear the queue. Now in this case, what we have done, let's come back to this slide now. I am writing a function called clear, which contains one argument called q, which is being pointed to by only one argument. Taking in C language a pointers variable pointing to a key data structure which we defined earlier, which contains some element, and front and key is a pointer. Now, so if does not contain anything, it means the front is pointing to nothing. If front is pointing to some element, it means some element has been stored. So clear means that front is pointing to null, means I don't have any element into the queue. Let's continue with is basically another function. This is function called each full function. This is one function. The purpose of this function is to return Boolean value. So right, so if function is full, means if all the elements are stored there, no position is vacant into the queue, it returns false, otherwise it returns true. Now here is the whether queue is empty or not. If queue is empty, how we'll check is again it simply returns true value when the front value of a queue data structure pointed to by PQ is equal to null. So when we say Boolean, it returns either true or false. So all this function is full, is empty, which we have defined earlier also, and you must see the logic has changed now, because here we are working with a different type of data structure now. Now let's move with another function, what we call delete queue. This is the most important function, delete queue and push queue or add queue. So delete queue is if queue is empty, then nothing to do, you can't do anything. Otherwise, this statement says that I am deleting the element from a queue pointed to by a front of a queue data structure by PQ and assigning them into the PX location, into a location pointed to by a PX, right? And accordingly, the next front value will be pointed to the next node, which is going to be deleted into the next cycle. So this way, and finally we are returning true if the deletion from your queue is successful. Same way, we are going to add element into a queue data structure, right? So basically here is two stages we are doing now. When you are trying to push the element, it might be the first node itself. So this is the basic, the node here, if PQ is empty, it means if no node has been inserted into the queue, then you basically you allocate a memory and assign and store the allocate a memory and store the data, and finally that is going to be part of that is going to be first node or first element of your data structure. So this part shows that the element which you are putting into the queue, it is the first element. When you try to add element into the queue data structure, the two type of situation. In the previous slide, what we talked about is, in the previous slide we see that if whether queue is empty or not. If queue is empty, that is going to be your first node. If queue is not empty, means they say that already some element has been stored into it, then accordingly it has to be adjusted into it. So the PQ reader will point to the element which you have inserted currently, and then its value has to be assigned, that is x has to be assigned to it, some value you have assigned to it, and finally that node is the last node that will be pointing to the null. So two stages we have pushed the elements now. Let me come to the conclusions now. We have covered two types of data structure. One is called a stacks and second is called queue, right? And all are basically list data model. You see the second row, and all the data models, a stack as well as a queue, we basically use two representation scheme. For a stack, we use array type of data structure as well as a linked list type of data structure, and for the queue, circular array type data structure as well as a linked list type of data structure. We used both dynamic data structure as well as what we call static data structure, or also called sequential representation for representing these two data structure. We also covered lots of different type of applications for a queue data structure as well as a stack data structure. These two are most useful data structure. In most of the algorithms and the program, you have to use them and write a good program or efficient program. This is all we wanted to discuss. Thank you very much.